Alright, welcome back everybody. In this video we're going to look at the last couple of examples from the parametric functions and derivatives lesson. We start by talking about how to find dy dx for two parametric functions, x equals f of t and y equals g of t. It's very simple. If we take the derivative of y with respect to t and the derivative of x with respect to t from the chain rule, if we just take dy dt divided by dx dt, that gives us dy dx. There's also a couple of other definitions up here. A parametric curve is considered differentiable if it's differentiable at every parameter value. In other words, can I find the value of the derivative at every parameter value? And the curve is smooth if both f prime and g prime are continuous and are not simultaneously equal to 0. Alright, so let's look at example 3 here. Find dy dx if x equals 3 cosine of t and y equals 2 sine of 2t. Is this curve differentiable? Is this curve smooth? Alright, so first of all, to find dy dx, I find dx dt. The derivative of 3 cosine of t with respect to t is just going to be negative 3 sine of t. And dy dt, the derivative of 2 sine of 2t is going to be 4 cosine of 2t, and so dy dx is equal to negative 4 cosine of 2t over 3 sine of t. Is this curve differentiable? Well, both curves were differentiable for all values of t. So, yes, this curve is differentiable. Is this curve smooth? Are these two curves individually continuous? Yes, and yes. Is there any value of t for which they're both equal to 0? Is the next question. How about t equals pi over 2? Negative 3 sine of pi over 2. Oh, no, it's not 0 there. I'm sorry, what am I thinking? Oh yeah, sine. Sorry, had a little bit of a brain fart there. Let's see, is there any value where they're both simultaneously 0? So we would need the sine to be 0, but the cosine of twice that value to be 0. And there is no such value. So, is this curve smooth? Yes. Alright. Below we see a parametric formula for the second derivative. To get the second derivative, d squared y dx squared, we're going to take the derivative of dy dx with respect to t, and then divide that by dx dt. Why does that work the way that it does? Well, figure that when we're trying to find the second derivative, d squared y dx squared, we're taking the derivative with respect to x of dy dx, and if I took the derivative with respect to x of the dy dt over dx dt that I had, alright, in order to get that to be equal to the derivative with respect to x of, well, let me rephrase that. What we're showing here is we're showing that we're taking our dy dx and differentiating it with respect to t. And because we're doing that, what we really have is we have d squared y dx dt here. And so in order to get this to be equal to d squared y dx squared, we need to multiply the denominator by a dx and multiply the numerator by a dt so that these dt's cancel out. And multiplying by dt dx is the same thing as dividing by dx dt, and that's why this formula works the way that it does. Alright, let's go ahead and look at an example here. Alright, part A. Find an equation for the tangent to the curve at the point corresponding to the given value of t. And part B, find the value of d squared y dx squared at this point for the given parametric function. So for part A, I want to find a tangent line to the curve. In order to find a tangent line to the curve, I need two things. I need a point and I need the slope. So I can get the point by substituting the parameter value into these equations for x and y. And so this tangent line is going to go through 1 plus 1 over 2 squared. The x value is 5/4. And 1 minus 3 over 2. So the y value of the point is negative 1/2. So there's my point. Now I need dy dx in order to get the slope. So I find dx dt. The derivative of 1 is 0. The derivative of 1 over t squared is going to be negative 2 over t cubed. dy dt is going to be equal to, let's see, that's negative 3 over t to the negative 1. So that's going to be 3 over t squared. And so dy dx is equal to 3 over t squared over negative 2 over t cubed. Simplifying this, we get that dy dx is negative 3/2 t. And so dy dx, evaluated at time equals 2, is going to be negative 3. That's the slope of my tangent line. And so my tangent line here is going to be y plus 1/2 equals negative 3 times the quantity x minus 5/4. Okay? Next, part B, I need to find the value of the second derivative, d squared y dx squared. So I'm going to take the derivative with respect to t of dy dx, and I'm going to divide that by dx dt. And the derivative of dy dx with respect to t is just negative 3/2. And the value of dx dt is negative 2 over t to the third. And simplifying this, we get 3t to the third over 4. And so the value of this at the point of tangency is going to be equal to this evaluated at t equals 2. So we've got 3 times t, 2 cubed over 4. And so the value of the second derivative at this point of tangency is 6. Alright, example 5. Find the points at which the tangent to the curve is A, horizontal, and B, vertical. Alright, so I'm first going to find my derivatives. The derivative of the x component is going to be negative 4 sine of t, and the derivative of the y component is going to be 9 cosine of t. Alright, so in order for there to be a tangent to the curve that's horizontal, that means the change in y at that time is 0. And in order for there to be a tangent to the curve that's vertical, that means that the change in x with respect to t is equal to 0 there. Alright, so for part A, when it's horizontal, I'm looking for where 9 cosine of t is equal to 0. And that happens for t equals pi over 2, 3 pi over 2, 5 pi over 2, etc. So t is equal to pi over 2 plus k pi. Everywhere there's horizontal tangents. And for part B, for vertical tangents, we're looking for where negative 4 sine of t is equal to 0. So where sine of t is equal to 0, which happens at 0 and pi and 2 pi, and so for all values of time of the form k pi. Alright, and just to kind of illustrate this further, if I look at this function, x equals 4 cosine of t, y equals 9 sine of t, the graph looks like this. Come on. And if I trace this graph at time 0, you can see there's a vertical tangent to the line there. And if I trace this around, we go to a horizontal tangent up at the top here at pi over 2. And if I keep tracing it around, you can see those repeating vertical and horizontal tangents along the curve. But that's how we're going to find out where that happens algebraically. Alright, this is the end of our lesson on parametric functions and their derivatives. See you guys next time. Have a great rest of your day.